Alright, chemistry. I said I wanted to start off going over these questions, which is page 162 of your review book. I'm pretty sure I wanted y'all to do everything from 11 all the way up to 21. I am going to go backwards, and the reason I'm going to go backwards is because 11, 12, and 13, these questions over here, require a little more work. I want to go over the simpler ones first, then work my way up to the more difficult ones. Most of the other ones are just definition questions, and then the equation ones are really like you need to remember kind of what's going on. So let's go straight definitions first. Let me look at number 21. So number 21 asks, when a substance is oxidized, Alright, we're not allowed to do anything with protons. Choice 1 and choice 2 are garbage. If you see agent, I told you to think opposite. So it's not going to be an oxidizing agent if it is oxidized. That means it has to be choice 4. Alright, what occurs when an atom is oxidized in a chemical reaction? Alright, oxidation. This was... Oh... No, this stinking ink to shape. Alright, relax. This was Leo says Gur, right? Leo means if you lose electrons. Okay, so 3 and 4 are out. It's oxidation. Oxidation number is the charge. It will go up because we're losing electrons. Alright, number 19. What occurs in the reaction below? Alright, let's focus on the manganese, the Mn. Alright, here, Mn is paired with oxygen. Oxygen is -2. There are 2 of them, so that's a total of -4 charge. So the manganese is a +4 on the left. It turns into MnCl2. Chlorine has a -1 charge. But by the way, to do this, I would be looking at the reference table. I would be... Can I zoom out, please? No? Okay. That's fine. I would be looking here. Right? And I realize this is like upside down. Or sideways, I guess. But oxygen has this charge here of -2. Right? So that's how I got the -2 here for oxygen. Chlorine comes second, means it has to be negative. It only has this -1 here. So that's how I got the, there it is, the -1 for chlorine. Because there are 2 of them, that's -2, so manganese is +2. So it goes from +4 to +2. Alright, well that means choice 3, choice 4 are off the table. If the number goes down, means we're gaining electrons. Gaining electrons is reduction. That's choice 1. What particle must be transferred from one reactant to the other reactant? I'm not moving anything other than electrons. Electrons are what actually gets to move from particle to particle, reactant to reactant. All redox reactions involve both the gain and the loss of electrons. You're not allowed to have only one or the other. You need both. Redox reaction is one in which reduction and oxidation occur at the same time. Correctly describes redox. Again, these are 3 of the same question. Oxidation reduction occurs because of competition for electrons. Alright, now 11, 12, and 13 are all versions of identify the redox reaction. Now, this was the thing that had 5 steps. Step 1 was label oxidation states. Step 2 was continue to label oxidation states. If you remember step 0 was look for the single replacement. Now, if I look at all of these, number 12 is the only one that has a single replacement. Choice 1 here is a single replacement reaction. That means it is automatically the redox reaction. It's just how it is. I'm going to give you another hint. Double replacement reactions are never double replacement reactions are never redox reactions. So if I look at number 13 and I look at choice 1, this is a double replacement because the barium and the sodium are swapping. That is off the table. It doesn't look like it, but number 3 is also double replacement. Technically it's more sophisticated, but it's sort of a double replacement. But I'll just look for literal double replacement. Choice 4 in number 11, right here. This is a double replacement. That's off the table. So like you can either choose single replacement, you can eliminate double. Alright, so if I look at number 13 is nice because this iron has a charge of 0. This sulfur has a charge of 0. The reason for that, they are elements uncombined with anything. FeS, well, they are combined with each other. That's +2 and -2, which means they both change from left to right. If you find a single element on one side of the reaction, and then it's combined with something on the other side of the reaction, that also means it's a redox reaction. So if we look here, see this? This chlorine is, there's a chlorine here, uncombined with anything, and on the left side it is combined with the hydrogen. That means that 2 is your oxidation reduction, that's your redox reaction. Right? Now, all of the other ones, it is a little more difficult to tell. Right? Number 12 is the most difficult to tell. Is this a redox? Right. Labeling each of these, if you label each of these, the only one in which, oh, that's weird. This notation is wrong. This 4 should be down here. It is. That's so bizarre. That's very bizarre. Sorry, I just noticed that. If you couldn't remember single replacement, fortunately, number 12's answer was the first one, so you didn't have to go very far to find that answer. But otherwise, you would have had to label every single element. Right? It is a little annoying. Step 0. Look for a single replacement. If you cannot find one, then try to find something like choice 2 in both, where you have an element on its own on one side, and it's combined with something on the other. And that will kind of shorten your process. The reason that means it's redox is because if it's individual on its own, it has no charge. If it's combined with something, it definitely has charge. So its charge is changing from left to right. Alright. Those questions. This is going to be a slightly longer video, just because I know all the things that I want to get through here. I'm pretty sure that I can get through all this stuff still, because this page and this page are all just definitions, and it's a couple of phrases. We're adding on to Leo Sesger. Also, there's a cheat sheet for those 2 pages, but we'll talk about that in a minute. This right here, we are talking about half reactions. And the implication with half reactions is that they are not full reactions. Half reactions only show oxidation or only show reduction, hence half, because the full reaction would be redox or both. Half reactions, unlike regular reactions, show electrons. So this is the first time we're going to see electrons in an actual chemical reaction. Now, half reactions are still chemical reactions, which means they must be balanced for both mass and charge. The charge has to be the same on both sides of the equation. It just doesn't have to equal 0. So it could be like +1 on one side and +1 on the other side, or it could be -4 on one side and -4 on the other side. They just have to be the same. It doesn't have to be 0 on one side and 0 on the other. It just has to make sure that it's the same on both sides. Right? So, based on the redox reaction above, What redox reaction above? Oh, this one. Okay, so it above, on the last page. I'll write it out off to the side here. So we had copper plus AgNO3. I guess I'll write this a smidge smaller. Oop, just kidding. Hello? Can I get the eraser, please? Thank you. Okay. Why are we struggling? Hello? Technology. Please, please. Don't mind this. Minor technical difficulties. There we go. Or not. Alright. Copper plus 2Ag NO3 turns into, good, we can still see that, Cu NO3 2 plus 2Ag. Alright. And we labeled this was 0, this was plus 1, this was minus 1, this was plus 2, this was still minus 1, and this was 0. So if you look, right, this copper goes from copper to copper plus 2. So copper 0 turns into copper with a plus 2 charge. Right. This is not balanced for charge. It's balanced for mass. I have 1 copper and 1 copper. But it's not balanced for charge. If I need to balance this for charge, I need to add 2 electrons to the right side. Is just a lowercase e with a negative sign, implying that it has a negative 1 charge. Now if I look, I don't know why that's happening. If I look, the copper starts with 0, ends with plus 2, but the thing is, the total charge on my left side is 0. If I didn't have the 2 electrons, the total charge on my right side would be plus 2, right? And I need the charge to equal on both sides. The only thing I'm allowed to add is electrons, so I need to add electrons to the right side. The other formula, the other half reaction looks like this. It's the story of the silver. So half reactions only tell the other story. So 2 silvers with a plus 1 charge. I'm leaving a bunch of space intentionally, turn into 2 silvers and a 0 charge. And this time I need to add the electrons to the left side. Right. This one here is oxidation with the electrons on the right. This one here is reduction with the electrons on the left. That will always be the case. If it's oxidation, the electrons will be on the right. They will be products. You're releasing them. If it's reduction, the electrons are on the left. You're absorbing them. You're taking them in. You're adding them together. All right. Now, I'm gonna ask you to do these 3 practice questions here. Give them a shot. You have to do 2 things. It says to write out the half reactions. First, label all the charges. Right. If there are charges labeled already for you, like there are here, then obviously you do not need to label charges. They are already labeled for you. However, see how this has nothing attached to it yet? You can label that one. Nothing is labeled here. You should label all of those. This is already labeled. Do nothing to it. These are already labeled. Do nothing to them, but you do need to label these. All right? Give those a shot tonight. That'll be the first thing I look at tomorrow. Spontaneous redox reactions. We'll talk about this when we talk about... I'll talk about table J when we talk about the chemical cells below. Alright, electrochemical cells, which are page 70 and 71, are devices that relate electricity and redox reactions. There are two types. They are voltaic and electrolytic. Alright, the type of cell tells you what it makes. Voltaic cells make volts, they make electricity. Electrolytic cells make electrolytes, they make chemicals. More on that in a moment here. So, the substance that gets oxidized, alright, this page refers to voltaic cells. So whatever it is that's oxidized is called the anode. The substance that gets reduced is called the cathode. And electrons will always go from anode to cathode. This is always true. This is always true. Anode to cathode. Voltaic cell uses what we call a spontaneous redox reaction, which means it happens on its own. It will always happen on its own. And the redox reaction will take place spontaneously because of how the elements are arranged on table J. Alright? So the anode and cathode, which one is which, depends on where they appear with relation to each other on table J. Table J is like a full-page table. Right, here it is. Table J is called the activity series. It's how active are they. And it goes most active to least active. Something I'd like you to write in. Most active. This is more likely to be oxidized. The higher up the metal is, the more likely it is to be oxidized. The lower down it is, the more likely it is to be reduced. Right? If something is higher, it's likely to be oxidized. It will be the anode. If it's lower down, it's more likely to be reduced. It will be the cathode. Now, maybe you remember that I said we were going to add some more phrases. Or at least another phrase, right? We said that Leo says grr, right? Now, Leo is a red cat. Leo is a red cat who is friends with an ox. Just go with me. Go with it. All right? Just go with it. Leo's a red cat. He's friends with an ox. He says grr. All right? Red cat is because reduction happens at the cathode. And ox is because at the anode, it's always oxidation. Anode, oxidation, reduction, happens at the cathode. Leo is a red cat. He's friends with an ox. Alright. With this example here, if you look, we have zinc and copper. So if you were asked what is the anode and what is the cathode, well, let's check table J. Zinc is here. Copper is all the way down here. That means zinc is likely to be oxidized. It's active. More active means more likely to be oxidized. Zinc is likely to be oxidized, so zinc is the anode. Copper is the cathode, because zinc is higher on table J than copper. That's more or less how to read table J. All right. Now, when we make a voltaic cell, which, by the way, is a battery is a voltaic cell, something that turns chemicals into electricity, we need to connect the two pieces with a wire in order for electrons to flow. So electrons flow through the wire. A device known as a salt bridge connects the half cells and allows ions to flow. The bridge is not a literal bridge, nor is it made out of salt. It's something that allows salt to move through it, salt being made up of ions. The salt bridge contains an electrolyte, which again is a fancy word for a salt. Not necessarily table salt, it's just salt. Right. The big deal with a voltaic cell, it converts chemical energy into electrical energy. Remember that electrons flow through the wire, ions flow through the salt bridge. Alright? If you remember nothing else, it's Leo says grr. Leo is a red cat that's friends with an ox. The reason red cat and an ox are important. Reduction at the cathode. At the anode, it's oxidation. And also, this statement down here. Electrons flow through the wire, ions flow through the salt bridge. Right? The last piece to this is about electrolytic cells, and you might be like, oh god, more notes. Kind of. We're just going to flip everything. So, instead of using chemicals to make electricity, we are going to use electricity to make chemicals. Right? In an electrolytic cell, a power or voltage source is used to force a reaction to occur. So what happens is it passes an electric current through the substance inside the cell, which we call electrolysis. This is a chemical reaction that it literally involves taking electric current and running it through something specific. Right? During this, ions of opposite charge migrate to the electrode, and a half reaction occurs. So we force positive things towards a negative, we force negative things towards a positive, we make this thing run in reverse. This is how you recharge your battery in your phone, right? So your phone battery works like a voltaic cell normally. When you plug it back in, the electricity from the wall forces a chemical reaction to happen inside of your phone battery, meaning that it can power your phone for another, 2 to 12 hours. Oxidation still occurs at the anode. Reduction still occurs at the cathode. And ox, red cat. Leo's a red cat. He's friends with an ox. Right? An electrolytic cell converts electrical energy into chemical energy. Again, the type of cell tells you what it makes. Voltaic cells make voltage. Electrolytic cells make electrolytes. There's some extra information here. Don't fuss over it. This is like your cheat sheet, right? If you remember nothing else from the last 3 pages, all this electrochemical cell, voltaic cell, electrolytic cell, you have this cheat sheet. Here's the last phrase. We had said that Leo says grr. We said that Leo is a red cat who is friends with an ox. They travel around in a van because Leo's friend the ox won't fit in a car. Also, in a voltaic cell, the anode is negative. V-A-N. Alright? In a voltaic cell, the anode is negative. If you can remember that one piece of information, that tells you everything else. Because if the anode is negative, that means the cathode is positive. So there's your voltaic information. For electrolytic, everything flips. If you know that the voltaic anode is negative, then flip it all for electrolytic. The electrolytic anode is positive. All right. I want you to notice oxidation always occurs at the anode. Electrons flow from anode to cathode. Our phrases will always be true. Right? Leo says grr. He's a red cat who's friends with an ox. They drive around in a van. All those things are just parts of the definition that will help you. The other piece, voltaic cell makes voltage, it makes electricity. Electrolytic cell makes electrolytes, it makes chemicals. The type of cell tells you what it makes, and then you have Leo says grr, red cat, and ox. They drive around in a van. Alright. I know today's video is a little long. I'd like you to do these questions here on 69. Make sure to do these half reactions. Alright, you're going to show electrons. So, what you need to do is label charges first, then only tell the story of the things that change charge. Right? This copper went from 0 to +2, which means we need to add electrons on the right in order to balance out the charge. The silver goes from +1 to 0, means we need to add electrons to the left to balance out the charge. Right? There will be a lab, I might do the lab after break as a review for after break. So again, I want to do the electricity test before the break. We'll do a couple example, actually there's a, no, we'll do I'll do a few examples of this before the test next week. We're going to pick up right here. If you look at the next page at 73, so 73, 74, 75, 76, 77 are all about the periodic table. It's all just about reading the periodic table. It's very straightforward. It's very nice. All right. Again, everything is downhill from here. So redox was the hardest part. Everything else is downhill. Everything else is straightforward. It's mostly reading and drawing pictures, which I'm confident that you guys can do. All right. Do those 3 questions, so 3 half reaction questions, and we'll go over those first thing next class. Till next time, kids. I'll see you.